Welcome back. This is the 7th week of this class on functional analysis. And this week we will talk about distributions and Sobolev spaces. We will start with distributions. And let's start with talking a little more on D. And we will see what D is and what its dual space is. So we'll start with an open domain omega, which is part of Rn. N is the dimension of the space Rn. So R1 is the line, R2 is the plane, R3 is the space we live in, and we can of course do R4, R5, or any Rn for any n, for any integer n. Now, D of omega will be the set of all functions that can be differentiated an infinite number of times and that are with compact support. And that is functions that the set, the starting set is omega. So this set, C0 infinity of omega, is also denoted D. Actually, it's usually denoted D in French books, but you will see that this definition, this notation, this French notation, has an impact on notation which is used all over the world. Now, D can be equipped with a topology. And the topology we will equip D with is this one. U is an open set if for all compact sets K and for all functions f in U with compact support included in K, then there exists an epsilon positive but not zero and a multi-index alpha such that the set of functions G that are elements of D of omega, such that the support of G is included in K, and for all x in K, the derivatives of f minus the derivatives of G for any types of derivatives, so this is where the multi-index notation comes into play, smaller than epsilon, is included in U. And I just would like to mention this part here with the derivatives so we all understand what we're talking about. Well, alpha is a multi-index. If alpha is basically a line of 0, then what we have is simply f minus g. But we can also have derivatives with respect to the first variable, second variable. So all of these derivatives need to provide me with the absolute value of this difference smaller than epsilon. So we have a topology on D, and the topology we have here is not the most critical thing to understand at this point to understand what distributions are about. Convergence in D. The sequence Fn of elements of D converges in D toward an element of D that will be denoted F if we have two things. Number one, there exists a compact set K such that for all n in n, the set of integers, the support of Fn minus f is included in this compact set K. And, second criteria, for all multi-index alpha, the derivative of Fn with this multi-index converges uniformly toward the derivative of f with respect to this alpha multi-index. And that is on the compact set K. So this provides convergence in the set D, or C0 infinity, which is the set of all functions that can be differentiated as many times as I want with compact support. Now, this set D has dual space that we could write, that we could note D star, but in very many French books, it is written or was written D prime, prime being the notation for dual space. Now, this dual space, D star or D prime, and from now on it will be D prime, is called the set of distributions. Now, this is not a course on distributions, so what I just said over the few minutes is not going to be a course on distribution. I'm just trying to give you an overview of what is a distribution, because I will need distributions. But I would like to say that there are a lot of courses, including on this platform, about distributions, and I encourage you to actually take these classes if you're interested in knowing more about distributions. Now, I'm going to give you an example of a distribution, and maybe we should start with this. Let's choose a function f in L1 log. And if you forgot what is L1 log, I suggest you review this in the videos where we define the LP spaces. Now, you choose f in L1 log, and I will define tf as a function from d to r. So you feed tf with a function of d, which will be phi, and tf of phi will be the integral of omega of f times phi. Now, tf is linear, and it is continuous, so it is an element of d prime. It is a distribution. So what I'm saying is that any function f in L1 log can be associated to a distribution tf, because I can just define tf of phi as the integral of f times phi. And actually, these distributions are specifically called regular distributions because they come from functions f that are defined this way. I'm going to give you other examples of distributions. Let's actually look at t from d to r defined by t of phi equals phi of 0. Well, t is linear. You can verify this easily. It is continuous, so it is an element of d prime. It is a distribution. It is called a Dirac. It is called a Dirac distribution. Some people call it the Dirac functions. It's a little not proper to call it a function, but why not? It is called a Dirac distribution, and what we have is this notation delta for the Dirac function or distribution. And as you can see, it is not in L1 log. So all functions in L1 log are basically distributions, but you can find distributions that are not coming from function in L1 log. Now, we define these distributions for a reason, actually. And the reason why we define distribution is so we can differentiate them, and we will see we can differentiate distributions as many times as we want. We won't have a problem to differentiate distributions. So I'll start with t, an element of d prime, a distribution. And I will define the derivative of the distribution as, well, actually this way. The derivative t prime of the distribution t will be the function going from d to r, such that t prime of phi is equal to negative t of phi prime. Now, for all phi in d, we can denote it this way, bracket t prime phi equals negative sign, bracket t phi prime. So the reason why this is a good definition is because if I choose functions in L1 log and I associate the distribution to this function, the derivative of the distribution is consistent with the derivative of the function. So that's very good. And that is because of the integration by part. Now, if you choose a distribution and you have a multi-index, the derivative of the distribution t with respect to this multi-index will be defined this way. d alpha of t will be defined such that it's negative 1 raised to the power absolute value of the multi-index. I'm going to talk about that in just one sec. T applied to the derivative with respect to alpha of phi. And for all phi in d, what we really have is this, with the brackets, which again is consistent with the derivative of functions. Now, let me show you what this multi-index is about. And if you look at an example, it's really easy to understand. Let's choose alpha equal to 1, 4, 5. 1 is in blue, 4 in green, and 5 in red. Here is what the absolute value of alpha is. That's 1 plus 4 plus 5, so that's 10. And as you can see, -1 raised to the absolute value, so to speak, of alpha is going to be -1 raised to power 10, so that's 1. And what we have is d1, the derivative with respect to the first variable, d2, the derivative with respect to the second variable that you do 4 times, so you differentiate the derivative of the derivative of the derivative, and I think I got this right. In any case, what you do is the fourth derivative with respect to the second variable, and the fifth derivative with respect to the third variable. And so what you have when you compute the derivative of the distribution is you apply this derivative to phi, and that is the same as actually applying the distribution to the derivative, and there is no negative sign because -1 raised to power 10 is 1. So I hope this helps you understand how you use these multi-index notations. Why is it such a big deal to have distributions? Because you can differentiate as you want. You have no longer have to worry about whether it is differentiable or not differentiable. And let's actually look at this example. F being defined as 0 if x is smaller than 0 and 1 if x is greater than 0. So what you have is this function here in red. Now, you know, if you do calculus, that you cannot differentiate in 0. You don't have a derivative in 0. Now, with distributions, you can differentiate. So you know this function f, this function is in f1, is in L1 log. So because f is in N1 log, it is a distribution in a sense. It can be associated to a distribution. And the distribution, you can differentiate it, and you can see that the derivative of the distribution is the delta function we talked about earlier, and you can verify this. Now, as a remark, LP is included in L1 log. So LP functions are regular distributions. So what you can do is now differentiate any function in LP, or we should say any distribution associated to functions in LP, as many times as you want. You don't have a problem to differentiate functions in LP anymore. And the derivative might be a distribution that is not in LP, but a distribution. So again, the good thing about distributions is that you can differentiate as many times as you want. You don't have a problem. Now, the question is, what happens when the derivative of the function in LP is in LP? Well, stay tuned for more. That's going to be the point of the next video.